Okay, so here I'm going to have you guys look at how to model with some quadratic functions. And basically what we're going to try to do here is come up with the quadratic equation that represents a set of data points that's behaving quadratically. So if you take a look here, you can see that our essential understanding is three non-collinear points, no two of which are in line vertically, are on the graph of exactly one quadratic function. That's our essential understanding. Remember, non-collinear means they can't all three of them be on the same line. And the second part is saying they also can't be lined up exactly vertically from one another. If that happened, obviously there's no parabola that goes through both of them. So any 3 points that I give you, there's going to be one parabola that goes through them. Okay, so let's take a look at this piece here, and then we'll get started. So let's say that you and a friend are tossing a ball back and forth, and you each toss and catch the ball at waist level, which is about 3 feet high. What equation in standard form models the path of the ball? Well, we know that there's different models for something like this, but you can model the path of that ball with a parabola, and its vertex is going to be at 0, 3, and maybe it has x-intercepts at -5, 0 and 5, 0, depending on how far apart you are and how high you're throwing the ball. And then by substituting those values of these 3 points into a quadratic equation, you could come up with the actual function of y equals -0.12 times x minus 0 squared plus 3. And then we could translate that into standard form as well. Okay? All right. So you've learned about vertex form and you've learned about standard form, and you can use either form to write the equation of a quadratic function given a couple of data points. So let's take a look at what you need to know. First, ask yourself if you know the vertex. If you do know the vertex, then you want to know, do you know another point on the parabola? If you know one other point and the vertex, you can use vertex form to actually find an equation, and we'll walk through how to do that in this lesson. If you don't know the vertex of the parabola, you need to know at least 3 points on the parabola, and if you know those 3 points, then you can use standard form and a little bit about systems of equations to find the actual equation ax squared plus bx plus c. Okay, so if you think about this, you want to write this function. The 3 things we need to know are a, b, and c. And remember that when solving a system, if there's 3 things that we need to find, there's at least 3 equations we need to set up. And that's why we need to know at least 3 points on the parabola. All right, so I'm going to walk you through some things here. And let's see, let me get rid of this notation over here. I want you to kind of read along with me, and we'll talk about how to do this. Okay? So if a parabola contains 3 points, 0, 0, -1, -2, and 1, 6, what's the equation of the parabola in standard form? So what we do is we substitute those x's and y's into the function y equals ax squared plus bx plus c to write a system of 3 equations. The 3 equations come from the 3 points listed right here. So for the first point, 0, 0, I'm plugging 0 in for y, or 0 in for x and 0 in for y. And if I do that, I get 0 equals a times 0 squared plus b times 0 plus c. Well, if I simplify this, I'm left with the fact that c must equal 0. Now I will admit this was kind of a special case because my vertex happened to be exactly at the point 0, 0. Then we'll use the second point, where x is negative 1 and y is negative 2, and do the same thing. Y is negative 2, x is negative 1, so we have a times negative 1 squared plus b times negative 1 plus c. Simplifying that, remember negative 1 squared is positive 1. We end up with negative 2 equals a minus b plus c. And then we're going to look at the third point and do the same exact thing. We're going to plug in 1 for x and 6 for y. So we end up with 6 is equal to a times 1 squared plus b times 1 plus c, where 6 is equal to a plus b plus c. Okay, so I said this was kind of a special case. And again, that's because it went through the origin, and it results in c equaling 0. Because c is equal to 0, then the system, when you plug in c equals 0 here and c equals 0 here, the system will reduce down to just these two equations. A minus b is equal to negative 2, and a plus b is equal to 6. Then you can simply use elimination. Remember, add the two equations together. A plus a is 2a, negative b plus b is 0, and negative 2 plus 6 is 4. So you can use elimination to solve. 2a is equal to 4, divide both sides by 2. A is equal to 2, and if you plug that back in, you'll get b is equal to 4. Okay? So substitute a is 2, b is 4, and c is 0 into standard form, ax squared plus bx plus c, and you get the parabola 2x squared plus 4x plus 0, or just y equals 2x squared plus 4x. Now if you want to, you can stop for a second and go to the graphing calculator at desmos.com and graph this equation and make sure that it actually contains these 3 points. It's a nice way to verify what we've just done here. Okay. In the second problem that we're going to look at, we're going to compare a couple of models. And campers at an aerospace camp launch rockets on the last day of camp. The path of rocket 1 is modeled by the equation h equals negative 16t squared plus 150t plus 1. And by the way, this is because of gravity. That's where we get this negative 16 coefficient from, where t is the time in seconds and h is the distance from the ground. The path of rocket 2, however, is modeled by the graph that you see in the picture below. Which rocket flew higher? Well, if we want to know which rocket flew higher, what we're really asking is, where does this highest point occur? And of course, that highest point is what we call the maximum of the quadratic equation. So what we want to do is find the maximum height of each rocket by using the models or the equations that model their paths. So to do that, we need to graph both equations. In both cases, the maximum will occur at the vertex of the parabola, right? So if we go back here for a second, we can kind of see the picture of this graph here. We can kind of approximate where that vertex is. It looks like it's at time equals 6 seconds, and it looks like it's pretty close to 600, but not quite. I'm going to guess maybe something like 575. So it looks like the maximum height is 575 feet, but I'm not really sure. So we're going to try to figure out what's the maximum of this equation and compare the two. Compare what we know. All right. So in comparing these graphs, if I want to find the vertex of that equation, I need to locate the line of symmetry. Remember that in any parabola, the vertex will be right along the line of symmetry. I know that's crooked, sorry. And if I know what that line of symmetry is, I'll have the x value for the vertex. I plug that in to go ahead and find the y value of the vertex. And this is just function notation to show how that works. we know that at the vertex, x is equal to negative b over 2a. And so that's your x value here. And your y value is what happens when you plug negative b over 2a into the function. And using function notation, the way we would write that is f of negative b over 2a. So let's go back and look at what the equation was again. I almost forgot. Oh wait, I did forget. Let's go back a page. Oh, nuts. So the equation was negative 16t squared plus 150t plus 1. I'm going to write that down. Negative 16t squared plus 150t plus 1. So we can see that negative b over 2a would result in 150, negative 150 over 2 times negative 16. And then we plug that in to get the y value as well. If we do that, we can identify that the vertex is at negative 16 and 150. Or excuse me, b is 150. If we do that, we identify that the vertex is at the point 4.7, 352.6. So the maximum height of that rocket was at 352.6 feet. All right. Now, I don't know for sure, but I was approximating. I said 575, close to 600. This is approximating it at 580. But it's pretty clear that whatever it is, it's much greater than 352.6 feet. So we know that rocket 2 must have flown higher than rocket 1. We know at the very least that it's more than 500. So we know for sure that it's greater than the maximum height of rocket 1. Now we're going to look at some data and hopefully using your graphing calculators to help you construct the equation of a quadratic that goes through some data that behaves quadratically. I don't know what I just did there. Okay. All right, we call that process on a graphing calculator, we call that quadratic regression. Regression is the process of finding an equation or a function that fits a set of data points. And of course, quadratic regression would be what you do when you want to get a quadratic or parabola that fits that data. All right, so in problem 3, we have some data that shows a meteorologist predicted temperatures for an October day in Sacramento, California. At 8, it was cool, 52 degrees. 10, it was 64. At 12, it was 72. At 2, it was 78. At 4, it was 81, blah, blah, blah. And so you can see that the data is actually increasing up to 81 degrees, but then it starts to decrease. So visualize what this would look like. Increasing, 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 increasing. How many is that? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, and then it starts to decrease. Now I don't know if when it's increasing like a line linearly or if it's increasing at a curve. So we would want to plot those points to see how that data is behaving. What you're going to do on your calculator, and I'll help you with this when we get our calculators out, but we're going to enter the data into some lists. So we're going to enter the x values into what we call list 1, and we're going to enter the y values into what we call list 2. I just want to give you the overview here. And then we're going to use the calculator regression function, the quad regression function. And when you do that, you use that function and you tell it to use the data in list 1 and list 2, and it will spit out these values for A, B, and C. And so what you would do is plug in those values for A, B, and C to get the equation. So you can see the equation down here gives you negative 0.469x squared plus 14.716x minus 36.121, and those are coming from your values of A, B, and C right here. The r² value is something that's rather interesting. The closer that value is to 1, the better the equation fits the data. And you can see if we graphed that data here, the circles represent the data points and the line represents the function. You can see that line actually goes through most of the data points. This one is a little bit high, but not much. This one's a little bit low, but not much. But it seems to fit the trend pretty darn well. So when you get to the point where you're ready to put this data in on the calculator, I can help you with that in class. Now once you've done that, you have that equation, you can use the equation to make predictions. There's really no point in coming up with an equation that models things unless you're going to use that equation to make predictions. So if we want to use our model to predict what the high temperature is for the day, then what we're really asking is, what is the vertex of that equation? And so if this is my model, we can see in our lists, plugging that model in, we could use the calculator to help us generate some values about what's happening in small increments. But we can see that the maximum occurs pretty darn close to 15.7. That's where it peaks at 79.379 degrees. It's lower on either side. Now this is kind of weird. 16 represents 4 o'clock, right? So 15.7 would represent about 3:42. That's an interesting problem in and of itself. And we can talk about that one-on-one as well. Okay, so what I'd like you to do now is a little bit of practice. You can kind of look at these problems here. I want you to be able to find an equation in standard form of the parabolas that pass through these points. Let's focus on question 7, 11, and 15. And I'll go through those on each slide and we can figure out what the correct answer is. So here's question 7. Find an equation in standard form that passes through these points. So do that now. Pause the video. I'm going to go through these to figure out which one is the right answer. Oh, it's not D. Oh, it's not C. Hooray! It's B. I hope that's what you got. Now pause the video and do problem number 11, and we'll find the correct answer. It's not A. It's not B. It's not C. It's D. Now that you've done a couple of those, 15 is the same. It's just written in a different format. If you look at 15, it's written in a table where we have the x's and y's here. So for example, this is the point -1, -4, of course. And if we look at 15, pause the video and try to find that equation. Not D. Oh, it is D. Hooray! All right, fantastic. Why don't you take a look also at problem number 16? That's another interesting problem that I would recommend thinking about. And let me know if you have questions on it. Now the next part that I want you to look at is problems number 19, or 19 and 21. 19 is kind of special because you have an f of 0. Anytime you have a 0, cool things happen. Well, I guess 21 we have that too, but sometimes it makes things work out a lot easier. So why don't we try number 19 and determine whether a quadratic model exists for the set of values. In other words, that means, do these values fit a quadratic equation? And if they do, try and find the model. So you need to graph these and see if you think a quadratic makes sense, and if it does, find its equation. Lastly, I'd like you to answer question number 28. A model for the height of an arrow shot into the air is h of t, where h represents height, is negative 16t squared plus 72t plus 5, where t is the time and h is the height. Without graphing, answer these questions. Without graphing. What can you learn by finding the graph's intercept with the h-axis? Now remember, this is h of t. That's like saying f of x. F of x, f represents the y-axis, x represents the x-axis. So if we're talking about the h-axis here, sorry that's so crooked, that would be here. And since it's h of t, t is the independent variable, so that would go along the what we normally call the x-axis. So think about, what could you learn by finding the graph's intercept with the h-axis, and how can you explain what that means? And what could you learn by finding the graph's intercepts with the t-axis? What does it mean in the context of the situation of shooting an arrow into the air? Answer those questions about what it means, what that graph would tell you about what's happening in this situation.